Call mathematics the purest form of knowledge. That's how I'd start. Sure, I know mathematics is the language of physics, which describes the world at its most fundamental level. But mathematics in its essence must be more. Mathematics conveys eternal truths beyond physical things, beyond human words. Mathematics is universal messaging that anyone, anywhere, from any culture can understand, even from an alien culture. For me, advances in mathematics represent advances in civilization, just like advances in technology, perhaps even more so. For Andrew Wiles to prove Fermat's last theorem is no less a crowning expression of human progress than for Steve Jobs to create the iPhone. How does mathematics advance? Certainly there must be many small steps, but also there must be breakthroughs. Breakthroughs in mathematics may seem like magic. What are they? How do they happen? How do they work? What are breakthroughs in mathematics? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. The best way to understand breakthroughs in mathematics is to speak with mathematicians and physicists who have made math breakthroughs personally and who have reflected on three questions: what math breakthroughs are, how math breakthroughs happen, and how breakthroughs work. I begin with a mathematician who is recognized for her breakthroughs in modern geometric analysis and awarded the Abel Prize for doing so. She is the first woman to be so honored. I go to the Institute of Advanced Study in Princeton to meet Karen Uhlenbeck. Karen, how do you distinguish between good, solid mathematics that are peer-reviewed papers and ideas that are legitimately recognized as breakthroughs?
Is I don't think it's necessarily immediately obvious when there's a breakthrough. It depends a lot on the outcome of the work. And if we actually could understand where mathematics was going and knew where things would lead, we would all be running after in that direction as hard as possible. But we don't know. So sometimes it's a longstanding problem. There was a conjecture called the Calabi conjecture. And this was solved by a very good friend of mine, Xingtung Yao. You know, there's rumors that he, holed himself up in his room for weeks on end until he got it. The solution was, interestingly enough, just straightforward hard work rather than a fancy kind of mathematics. But I don't think anybody knew what would come out of the Calabi conjecture once he solved it. You go and talk to a physicist, everybody knows what a Calabi-Yau manifold is. And of course, because it was important in physics, mathematicians actually spend a lot of time looking at it.
And was the fact that it had an impact in physics a critical step in the process?
Yes, because physicists come and bring a different kind of imagination to thinking about what you should do. And the observation over my lifespan in mathematics is that getting pushed in a slightly different direction tends to do mathematics a lot of good.
And so tell me the breakthroughs that you've made so I can try to understand it.
Well, the one that's easiest to describe is the question of minimizing two spheres in dimension spaces 3 through any number of dimension spaces. These spaces are complicated. They look locally like Euclidean space, which is just coordinates, but they are curved. And a typical example of such a space is the 3-sphere. If you think of the example of the 2-sphere with the geodesic around the middle, well, if you take the standard 3-dimensional sphere, the same picture 1 dimension up, then it's got a 2-sphere around the middle of it. And that's locally area minimizing. Not globally, because you could shrink it down, but it's locally area minimizing. So the question was, can you do this on a 3-dimensional sphere with any distance function on it? Is there such a locally minimizing two-dimensional sphere in it. And the theorem that I proved with Jonathan Sachs, who, by the way, was a postdoc of mine. And really, I often forget to say how indebted I am to him, because I wasn't thinking about the problem, and he came and started telling me about what people were thinking about, and I realized that this was a problem. And when we got together and started working to it, the solution of finding these locally area minimizing two-dimensional spheres was actually not that difficult a problem. See, I came to it with a background in thinking about such problems, and I met someone who told me what the questions were. And then we actually solved the problem completely unexpectedly. And I don't think at the time that it was recognized immediately as an important result, but I have to tell you quite honestly, it's totally amazing to me. But I go in, there's a special year here at the Institute for Advanced Study, which is studying minimal area objects of higher dimension. And it's very interesting how many times I've gone into a seminar and they have actually written Sachs Uhlenbeck on the board as being the beginning of the thinking about this problem. It's totally amazing to me. I mean, that this should still be an important theorem after all these years. So.
To Karen, breakthroughs are recognized only after a time, based on their outcomes, where they lead, what subsequent work they catalyze. Here at the Institute, breakthroughs in math catalyze breakthroughs in physics, and surprisingly, breakthroughs in physics catalyze breakthroughs in math. That breakthroughs in math and physics can trigger each other leads me to only one person. I meet the first physicist awarded a Fields Medal, considered the Nobel Prize of Mathematics, Edward Witten.
It's a little bit surprising, but the laws of nature have turned out to be mathematically interesting. For example, Einstein's theory of gravity, it involves curvature of space-time. And of course, you could study curved spaces purely as a mathematical subject, but understanding that that bit of mathematics was applicable to the real world gave a huge boost to the whole study of curved spaces. Near the end of my graduate school days, a breakthrough was made in understanding the standard model that involves something called the instanton of gauge theory. The instanton is a peculiar quantum event described by a classical solution of the gauge theory equations. And the equation it satisfies was unknown to mathematicians, but was mathematically interesting. It led to a lot of subsequent work. For example, my colleague Karen Uhlenbeck, her famous work involved the study of this equation. So what they did was to discover that if you want to understand four-dimensional spaces, you have to use this instanton equation that had come from physics. Well, first of all, why are you interested in understanding four-dimensional spaces? As a physicist, your answer is that we live in four space-time dimensions. But mathematicians, in principle, study spaces of any dimension. They made the surprising discovery that the four-dimensional case is in many ways the most interesting. Geometry is simpler in one way above four dimensions. It's simpler in a different way below four dimensions. Four dimensions is the most subtle case. And it turns out that this most subtle case, at least with the best understanding we have today, to understand it requires these equations, the instanton equations that came out of the standard model. And now, by about 87 or 88, that understanding had reached to the point that a very famous senior mathematician named Michael Atiyah had a vision of a new kind of relationship of what the mathematicians were doing with physics. And when he visited the institute, he posed to me the problem of understanding what's called Donaldson theory in a physics language. So it looked difficult technically, but eventually I had the good luck of noticing that if you made a little twist of the physics theories, where here twist is actually a technical term, you could recover what the mathematicians were doing. So that gave a physical interpretation of Donaldson theory of four manifolds, which was interesting. And I thought maybe it was going to lead to dramatic progress in the near future, but it didn't. But what I learned eventually was that anything a physicist could do that involved standard methods, what we call weak coupling methods, would just involve retracing the steps taken already by the mathematicians. To learn something really new, you had to do the hard part, which is to bring strong coupling to bear on this problem. But by 1993, my colleague Nathan Seiberg here at the Institute for Advanced Study was introducing new ideas about strong coupling. And because he knew about my interest in Donaldson theory, and because he probably didn't see an immediate way forward, but suggested it was possible to have progress there, he talked to me about it, and we started working on it. And by 1994, we developed what maybe was my most satisfying contribution to physics, what a physicist would call a new strong coupling approach to the supersymmetric gauge theory in question. But for mathematicians, we were actually able to predict for them a more powerful way of studying the four-dimensional spaces, what they now know as Seiberg-Witten theory. This was certainly something in pure mathematics where we were able to tell them something that they didn't know, although, there's always many different paths.
I appreciate Ed's personal story of his mathematical breakthrough. What to casual observers may seem to be sudden, explosive genius is, in reality, a rich human saga of discourse and struggle. Ed's breakthrough was a new approach to fundamental physics that also gave mathematicians a novel and more powerful way to study four-dimensional spaces. It happened after a long process of research and interactions. It works because of a deep structural connection heretofore hidden. Would similar principles hold across different areas of mathematics? I meet an expert on probabilities and statistics, Columbia mathematician Ivan Corwin.
With many years, behind you, you can look and see what type of results really changed a field. What was an inflection point? What was a turning point in a field? And then you can call them breakthroughs. But oftentimes, I don't think that's the right way of looking at it, because in the wash of history, you forget all of the other works that were leading up to it. You see these singular points that people call it breakthroughs.
Well, let's just look back historically. That what would you clearly say are breakthroughs in the past?
In probability, I would say something like the understanding of the law of large numbers or the central limit theorem. This notion, these sort of fundamental notions of probability can be seen as breakthroughs. And in fact, they're so fundamental that they were seen as breakthroughs multiple times. Different people proved them hundreds of years apart without realizing it. And each time, in a sense, it was a breakthrough. Because it's a mode of thinking. And more recently, of course, a very popular example is the proof of Fermat's last theorem, a very big theory that had been around for a long time and was proved in very fundamental and seemingly work that changed a field.
How about in your own work? Would you characterize any of it as breakthroughs, even if they're mini breakthroughs?
No, of course not. If I had to identify, so there is one thing, for instance, when I was a graduate student, we solved a problem which had been around for about 25 years. It was a big conjecture in kind of mathematical physics. And, people, I think, saw it as somewhat of a breakthrough. But I don't really see it as a breakthrough.
Well, so let's analyze why. I mean, when you did that, why did some people think it was a breakthrough?
Well, it sparked a lot of activity. It sparked a lot of interest, and it solved an open problem. But
so those are two interesting characteristics that might define breakthrough, even if
right.
So one is it solved an open problem,
yeah,
and second it catalyzed other kinds of activity that emerged from it.
So it was a paper from 1986 that we solved a problem, a conjecture that had been out there in physics, actually, and that paper gets a lot of credit. And interestingly enough, that paper really built off of a paper about 10 years earlier, which really did something innovative that doesn't get nearly as much credit. And the credit that this 1986 paper got was by the fact that it really popularized it. So sometimes, breakthroughs come down to what people later on push and popularize. And that's kind of why I don't think it's the right thing to focus on. I feel like math is much more collaborative. Sometimes a breakthrough is just a matter of bridging two fields, right? And a lot of my work deals with this type of question of relating, on the one hand, a very probabilistic look at the world, view of the world, to more algebraic structures, things like representation theory and symmetric functions. Neither of these fields are well developed, and so a breakthrough is bridging the gap, is connecting the fields. and then, shuttling ideas across.
Ivan characterizes mathematical breakthroughs in 3 ways. 1, solve an open problem. 2, catalyze new work. And 3, bridge gaps and connect fields. These reinforce what math breakthroughs are, solve and catalyze, and how math breakthroughs work, bridge and connect. I fear falling into a trap of confining mathematical breakthroughs to equations and formulas. I should explore a different kind of breakthrough, one that is less abstract, more philosophical. I meet a pioneer of algorithmic complexity, a key concept in computer science, Gregory Chaitin. Greg, you've written that Gödel gave us incompleteness, Turing gave us uncomputability, and I, meaning you, have given us randomness. Now, I know what randomness is, but your randomness is different. It's a new kind of randomness?
Yeah, I'm interested in, shall we say, mathematical results that have a big philosophical impact. And Gödel's 1931 result on incompleteness, Turing's 1936 result on uncomputability are just stunning paradigm shifts. They reveal a new world.
Okay, so then how do you take the next step in terms of defining randomness?
So the next step was, when you look at this notion of a computer as a mathematical, 1936 Turing's paper, it's sort of natural to ask how much time a computation takes, or how much information, what's the size of the computer program. These are sort of natural measures of complexity. And right away, one would like to prove theorems about runtime complexity or about program size complexity. So I was one of the first people to publish in this area. Subsequently, I stopped working on runtime, on the time a computation takes. I'm more interested in, which I think is more philosophically pregnant, I'm more interested in looking at the size of computer programs, which I think has deep resonance with some very important philosophical issues that can be traced back to Leibniz, believe it or not. So the first step, in the 60s, I was a teenager, is the notion of structural randomness, which is different from probabilistic randomness. That you get, if you toss a coin, independent tosses of a fair coin has equal chance of being heads, equal chance of being tails. The next toss has no connection with the previous tosses. Okay, that's the normal probabilistic notion of randomness.
Yes.
But the kind of randomness I'm interested in is structural randomness, or logical randomness, total lack of structure. So how do you define that? You define that as a string of zeros and ones, a finite string of zeros and ones, for which there is no more concise description, algorithmic description, than the string itself. Yeah. So if there's a small program, that means a concise theory that explains exactly bit by bit a sequence, then that's not random because it's compressible. So that's like a set of empirical data for which there is a good theory. It's a compression.
So does that mean that structural randomness is like an anti-compression?
Yes. The most concise way to transmit this information to someone is just give it bit by bit. There is no more concise description. There is no theory that explains this data. Patternlessness was the term I used.
Oh, that's a good term.
And it turns out that most sequences of zeros and ones are totally unstructured and cannot be compressed into a theory or a program to calculate it that is more concise than they are. Why? Because there just aren't enough small programs to go around. There are too many n-bit strings, programs, descriptions, algorithmic descriptions, concise descriptions that are smaller. There just aren't enough. So the great majority cannot be compressed. And this is a notion of structural randomness. It's a new kind of randomness. It's not like physical randomness. So this is a different kind of randomness.
Greg's breakthrough takes a commonplace idea, randomness, and applies it not to events, but to structure, thus enabling information compression and efficient computer programming. Given diversities of breakthroughs, could there be another kind of organizing principle for what breakthroughs are, how they happen, how they work? An organizing principle that relates the driver of the breakthrough to whether math generates the problem or math solves the problem. I turn to a favorite thinker who has followed mathematics from physics to biology, polymath Paul Davies.
There are really two sorts of theoretical physicists. There are those that just love the mathematics and they look for obscure relationships and then try to find something in the world to fit it, and that's all fine. But I'm in the latter camp of those who look at the world, are puzzled by something, and think, what type of mathematics do we need to solve that problem? Einstein was in the latter category. He spotted that he needed to describe some sort of warped or curved space-time, cast around for the mathematics that would do that, found it already existed, and with the help of colleagues, put that together into his general theory of relativity. People think Einstein was one of the world's great mathematicians. He wasn't really that wonderful at it. And, he once said about his special theory of relativity, I don't understand the theory of myself. Now the mathematicians have got that.
That really is a tremendous insight to the nature of breakthrough, because his simple conceptual thing, what it was like to ride on a photon, and then he had to search for the mathematics and then learn it and have other people who knew more about it to help him.
That's right. And now we live in an age where some people are having to invent new types of mathematics to describe their latest wonderful ideas, and string theory is one very good example of that. And so when you look at the history of physics and mathematics, the two are inspiring each other. And during my career, I have never actually had a problem in identifying what mathematics I need to solve a particular problem until now. And now, when I'm interested in the crossover between physics and biology and the possibility that there are new types of physical laws in which the way in which a system behaves might change depending on the state, the mathematics to describe that really doesn't exist. And so we increasingly use computer models where you can put in by hand the effect you want. But you see, this raises the whole issue about what is mathematics in this modern computer age, because in the past it was all about solving the equations. You had to be brilliant to come up with new solutions. Now, I think a lot of science takes place with computer modeling, and that always seems to me a bit of a cheat, but I suppose I'm rather old-fashioned.
Does it potentially differentiate problems in the world into two broad camps? One that can be described rigorously by mathematics because that's the way the world works. Then there are other problems which are messy problems.
It would be naive to suppose we could write down and solve a set of equations that would describe exactly what, say, a hurricane is going to do, or the way a complex neural network like we have between our ears is going to work. The very best we could see some underlying regularities, but it would be an exercise in statistics and enormous computation. So we're increasingly resorting to the use of computers to solve those physics-type problems. But also people are resorting to computers to solve mathematical problems. And the famous one, the four-color problem, can you color a map in such a way that four colors is enough, that you don't ever have two adjacent countries with the same color? That was solved quite some years ago now on a computer. So the computer sort of went through all the different possibilities and delivered the answer, but somehow that seems unsatisfactory to me, that there isn't a mathematician that can put it all together and think, aha, now I see how it works. It's just a machine telling you, well, okay, clever humans can program the machine or they can input the problem, but you take the computer's word for it and move on. We're losing something in that process.
Mathematics drives understanding, and breakthroughs drive mathematics. So, what have I learned? What are mathematical breakthroughs? How do they happen? How do they work? Mathematical breakthroughs take time to be recognized. They are assessed by their outcomes. That's what they are. Mathematical breakthroughs have stories. They build on the work of others. They meander. They are ignited by flashes of genius. That's how they happen. Mathematical breakthroughs solve open problems, bridge gaps, connect fields. Mathematical breakthroughs can transform commonplace ideas. They offer fresh insights, reveal deeper meanings. Mathematical breakthroughs occur both intrinsically, purely within math itself, and extrinsically, as explanatory descriptions of the real world. That's how they work. I myself will never make a mathematical breakthrough, but I love trying to figure out how mathematical breakthroughs can bring us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.